Great. Okay, so thank you everyone for being here. Today, as Indu said, I'm going to be talking about the asteroid Bennu and data from the OSIRIS-REx mission. So for this project, I'm going to give you first a brief overview on the OSIRIS-REx mission and this asteroid Bennu. I'll then be talking to you about the creation of machine learning spectral models, and finally, the application of those models to remote sensing data. So OSIRIS-REx stands for Origins, Spectral Interpretation, Resource Identification, Security, and Regolith Explorer. And my work falls under the Spectral Interpretations category. So this is an image of the asteroid Bennu that I'll be talking to you about today. This asteroid is a near-Earth asteroid. It is also a B-type asteroid classified by the visible near-infrared. It is a rubble pile. You can see here that we have a lot of different size particles here. We have boulders and then fine particulates. We don't have large ponds of fine particulates as we expected before arriving at the asteroid, which made sampling this asteroid more complex. And lastly, this is a very dark body with a very low albedo. So these are a series of images of the sampling event of this asteroid. So you can see this is the touch and go arm that is approaching the asteroid and then collecting sample. This sample will be returned this year in September. So what do we believe that this asteroid is composed of and this return sample will be made of? We believe it is analogous to a Ci, Cm, Cr, and or ungrouped carbonaceous chondrite. So what does this mean? We think that this asteroid is made of organic compounds. It has few or no chondrules in it, these millimeter-sized globules of refractory silicates, and it is primitive in nature. So these materials are really important for studying early solar system materials and early solar system processes. And then we know that these minerals that compose these materials have been altered by aqueous alteration. So today I'm going to be talking to you about OSIRIS-REx thermal emission spectrometer data. So this is the instrument on the left, and on the right, we're looking at the average spectrum from this instrument of the asteroid Bennu. So in the center of this this diagram, we have the silicate stretching region. We also have a detection of the mineral magnetite at 555 wave numbers and a feature at 440 wave numbers associated with phyllosilicate minerals. So now I'm going to transition to talking to you about the creation of the training set and machine learning models. So the objectives of this work were to create models to quantify the composition, specifically the mineralogy of this asteroid Bennu, and then apply these models to individual OTES spectra for the prediction of this mineralogy of this asteroid. So the first step of this work is to create a training set of samples. So this included pure end member minerals and then mixtures of those minerals that are representative of these compositions we expect Bennu to be composed of. I also utilized meteorite spectra within this training set of samples. Another factor that we needed to consider was particle size. So considering both fine and coarse particulate materials, this is important because in the mid-infrared, these different particle sizes behave differently with linear and non-linear mixing behaviors. I also darkened the samples that I was working with. So although we're looking at the mid-infrared versus the visible near-infrared, albedo does still affect these mid-infrared measurements. So as I've said, these measurements were made in the mid-infrared or the thermal infrared, and this was particularly important to look at the mineralogy and then apply these models to remote sensing data. And lastly, I utilize machine learning multivariate analysis in this work, specifically because it does not assume linear mixing across wavelengths. So the setup for these measurements, these samples were analyzed in the planetary or asteroid regolith spectroscopy environmental chamber, PARSEC, at Stony Brook University. These samples were placed in the chamber and measured at vacuum with a cooling of the environment and heating from both above and below to induce a thermal gradient. These measurements were made like this to simulate airless body measurements like Bennu. So this is a summary of 317 unique spectra that I produced for this training set. These are color-coded by phyllosilicate content. So after collecting the spectral training set, I used two types of machine learning, multivariate analysis, partial least squares, and as we heard in our previous talk, least absolute shrinkage and selection operator, LASSO. So when we compare these two techniques, PLS utilizes all available channels within the spectra, whereas LASSO optimizes which specific channels are most predictive. So in testing these two techniques, I found that PLS for these specific data outperformed LASSO. And a reason for this may be due to the fact that mid-infrared spectral features are broad in nature, and so having more utilization of more channels was ultimately likely more helpful. So I just wanted to talk a little bit more of an example of one of these PLS models. So you can see these have individual coefficients associated with particular metadata categories, in this case, minerals. And other than a small region around 1,300 wave numbers where I specifically cut out data, the entire spectrum is utilized in these models. This is an example of the number of components that go into the models. So I tested the number of components from 2 to 20. You can think of this as affecting the model's performance, in that choosing too few components may make the model less effective, but choosing too many components will make the model less applicable to data outside the model. So I chose specifically in this example the number of components where the mean square error is lowest. These are my internal model results for phyllosilicate minerals, olivine, carbonate, pyroxene, and magnetite. We see that we have high R-squared values and a good one-to-one relationship between our actual volume percentages and our predicted percentages. I also have here a root mean square error for these different models. I tested additional types of root mean square error with holding data outside the model, having unseen data. I'm not going to go into this in more detail, but it's an important part of this step. So after creating these models, I applied the models to global average spectra of Bennu. You can see on the left, I have a global average spectrum, and then comparing those to meteorite spectra, or meteorite quantitative abundances of the mineralogy through quantitative XRD. So when we compare Bennu to materials we expect it to be similar to, we have comparable phyllosilicate predictions with high carbonate and high magnetite predictions. So these are the conclusions of this first part of this work that I've just gone over. This section of this presentation was published in 2021 in the Journal of Geophysical Research, Planets. So moving on, I'm going to talk now about the application of these models to the remote sensing data, and specifically individual OTES spectra. So as a reminder, when we think about the training set, I evaluated I utilized a wide range of minerals in creating this training set. But for this section of the talk, I'm specifically going to be focusing in on the phyllosilicate minerals, which are clay minerals. So specifically magnesium-rich serpentine, kronstatite, which is an iron-rich serpentine, and lastly, saponite, which is a smectite mineral. So in this work, I utilize the baseball diamond 1 station data from the OTES data. These spectra were collected at local solar times ranging from roughly 9 a.m. to roughly 4 p.m. And these measurements were made at a heliocentric distance of roughly 1 astronomical unit. So these are some of the warmest spectra that we collected during the mission, and that really translated to high signal to noise ratios. So in this diagram, this is a summary of the prediction abundances for magnesium-rich serpentine, kronstatite, and saponite. For the baseball diamond 1 data that I'm focusing on here, these are shown on the left. So we have the highest prediction of magnesium-rich serpentine, followed by kronstatite, and finally saponite. So here I'm looking at comparisons between the first and the 99th percentile average spectra. So in this case, in red, we're looking at a spectral average with the lowest prediction of magnesium-rich serpentine. And in blue, we're looking at the 99th percentile average, or the spectra with the highest prediction of magnesium-rich serpentine. Although these spectra look similar, there are some differences between them. So we see band depth differences within the silicate stretching region. And one important thing to note here is some slope differences between roughly 700 and 500 wave numbers. So now we're looking at a different diagram. These are the predictions of kronstatite. So again, we see some similarities, but differences between these 99th and percentile and first percentile averages. So the biggest difference here we see is a difference in band depth for the 440 wave number feature associated with phyllosilicates. So for saponite, I did not observe spectral variability between this first and 99th percentile average. And why may this be the case? So some possible reasons include that the machine learning models did not isolate its spectral variability. Alternatively, the saponite content could be too low to cause spectral variability. Or lastly, the saponite content is relatively homogeneous across the asteroid. So this is a really exciting figure. This is the first mineral map using these data. So this is a map of magnesium-rich serpentine. So high predictions are shown in yellow and low predictions are shown in blue. We can see that lower predictions are centered around the equatorial region of this asteroid compared to the middle latitudes. Here, we're looking at a map of kronstatite, so this iron-rich serpentine. And in this case, we see high predictions in yellow centered around the equatorial region, opposed to lower predictions in blue in the middle latitudes. So we see an inverse relationship between the prediction of these two variables. So what might be going on here? I referenced earlier talking about aqueous alteration. So this is a process that occurs for these materials, which is the conversion from anhydrous silicate minerals to hydrated silicate minerals. And a detail of this is that serpentine-rich materials with a higher magnesium to iron ratio have a higher degree of aqueous alteration than those with a lower magnesium to iron ratio. So another component of this is how specific materials within carbonaceous chondrites are what they're composed of. So for matrix materials, they're primarily composed of iron-rich phyllosilicates, as the matrix materials are more susceptible to fluid attack, whereas chondrules are more rich in magnesium, chondrules include magnesium-rich rather than iron-rich phyllosilicates. And this is because of progressive alteration that transitions from iron production to magnesium-rich phyllosilicate production. So in trying to understand why we have these compositional differences across the asteroid, I looked towards Jowin et al.'s work reporting mass movement towards the equatorial region of Bennu. And I've tried to understand this in this process, potentially also causing this spectral variability that I observe. So processes that have led to the spatial variations in thermal inertia and this mass movement may also have caused mineral fractionation through physical processes enabled by initial variations in crystal size, specifically that matrix material versus the chondrules. So one last detail I just wanted to talk about was Nightingale, which is the sampling site of this asteroid. When I made predictions of magnesium-rich serpentine and chondrite at this site, they're roughly equivalent to the average surface of Bennu. So I believe that this return sample from the asteroid will be fairly representative of the asteroid as a whole. So these are the conclusions from this second part of this talk. And I'll just say that this work is published in Geophysical Research Letters this past year. So with that, I will take any questions. Thank you.